questions about the coursework or anything else? Life, software engineering, software development jobs. Anybody like the industry lecture and the industry stuff? Now you're all looking forward to graduating. Do you have a question?
Can you explain about the patterns? I mean, MVC and others patterns.
Can I explain about the design patterns? Anything in particular? Probably about how they relate to the coursework,
Yes.
for example. So the coursework asks you to use the model view controller pattern. If I was doing this, I would have 3 packages: a model package, a view package, and a controller package. All of the user input, like Java Swing and Java FX, anything associated with user input, like the file menu and buttons and things like that, I would put in the controller package. Anything associated with output, that's what the program is outputting graphics. So things like the movement of the ball and the bricks and maybe some other things, I would put that in the view package. And then anything associated with data, for example, keeping the high score permanent, I would put that in the model package. And there is some overlap with visual applications. There's overlap between the view and the controller, because like the paddle, for example, is both input and output. You're controlling the paddle with some input, but the paddle is also output because it's something you see moving back and forth. So whether that goes in the view or the controller, I would probably put it in the view package along with the other things, but there is overlap there. So it's not always black and white. And you can see in software engineering, lots of things are not black and white. Does that answer the question?
It means if I use both the single patterns and MVC, that I need to put my single patterns into the viewer package?
There's no rule about that. The example we gave when we talked about the singleton pattern was for a database, to make sure that like a 30 terabyte database doesn't get copied by accident, for example, or or when information about one thing has to be kept in one place and you want to make sure that it's never duplicated. In this case, there's no rule that says the singleton pattern must be used here, here, or here, or in the view class. It could be in the view package, it could be in the controller package, it could be in the model package. Most likely it would be in the model package, because there you store data, and usually you only want one copy of your data. But I personally don't think the singleton pattern is absolutely necessary in this assignment. Yeah, you can.
Just an example, I guess. Okay.
Any other questions? I have been getting a lot of questions about the MVC stuff, generally speaking. Any others? Thank you, by the way, for coming today. I shouldn't have to say thank you. You guys are the ones paying for this. Today's lecture is a special lecture, just like the one on Tuesdays. This is not testable material that I'm going to talk about today, because it's too advanced. And I'm not expecting everybody to be able to follow everything I say today, because some of the concepts here are very advanced. For example, master's level and PhD level concepts. However, I think you will follow some things, you will learn some things, and when you start to, maybe some of you might go into the future and take things like computer graphics or data visualization or image processing, things that are very visual. This is all about the visual computing. Like what we're talking about is visual debugging techniques for visual computing applications. You guys haven't gotten that far yet, but you are working on a visual game. A game is a visual program, right? It's a computer graphics subject. Computer games and computer graphics, right? They go hand in hand. So there is a little bit of overlap, but I don't expect everybody to follow everything I say today. You can also interrupt me and ask questions. You might, in the future though, take computer graphics or data visualization or image processing later on. You might even write a master's degree or a PhD in those subjects. I'm going to record this lecture, I'm putting it on YouTube, and you might be able to look back on it in the future and then understand, oh, now I understand what Bob was talking about sometime in the future as well. Has that happened to anybody where they didn't understand something the first time and then they saw it the second time and it clicked? That's happened to me several times, maybe even the third time. That's never happened to anybody else but me. I'm a slow learner. Yeah, so let's talk a little bit about visual debugging strategies. This is just a summary of the strategies. Like, there are lots of them, right? Visualize tests and comparisons, visualize data structure, traversal and evolution, classify and color map, incorporate algorithm parameters into the GUI, run simple error checks, introduce a step function, make use of still image driven animation, test on a variety of data sets. That's something that everybody can understand, right? Exploit and compare with previous literature. That's something that everybody can understand. Make exclusive use of accessor methods. That's something everybody here understands. Follow coding conventions. Describe the problem to others. I put in number 13 here so I wouldn't forget it. This is not really advanced at all. But a good debugging strategy is not to make too many changes at the same time. A lot of people in this module have come up to me and said, I've just changed 1 million lines of code, but now my program doesn't run anymore. Please help me. Like, that's not a good strategy. Don't change 1 million lines of code at once. Change 1 line of code, hit the compile button, see if it compiles. Maybe change 2 lines of code, hit the compile button, run it and test it. So you know exactly, if you run into a problem, you know exactly where it is, right? If you change 10, 20 lines of code or lots of methods at the same time, you can easily get lost. And by the way, I'm speaking from experience. I've made all the mistakes, right? So I'm not excluding myself. And all of these guidelines are based on experience, based on my own experience and based on reading literature. Like, I've read a lot of literature on software engineering, visualization, for example. And I've spent many years developing visualization algorithms and software in industry, not just academics. And why am I giving this lecture? It's because I like it so much. I know that's weird. I love this topic. And my brain is always working on these topics, like how to visualize program behavior, how to visualize software behavior, how to debug the programs, because I've run into some extremely challenging problems before. And then I felt like, okay, I have these ideas about how to debug these programs. I'll write it down, and present it. So in the future, right now, doesn't seem that way, but in the future, and it's not very difficult to imagine because you're all using mobile phone apps with massive amounts of data. The more data you're processing, the more difficult it gets to debug your software. right? And it's not too difficult to imagine trying to debug software that processes megabytes, gigabytes, or in terabytes eventually of data, right? And a lot of software uses very complicated data structures. We haven't gotten there yet in the second year to use really complicated data structures. We're basically sticking with simple ones like linked lists. But this stuff works on just simple data structures too, like linked lists, for example. And traditional debugging tools decouple the information they report with the spatio-temporal domain in which unexpected problems occur. That means, imagine you're looking at your bricks, what is it called, this application, bricks? Is that what it's called? The one we're working on for the coursework? The bricks program, break a brick or whatever it's called. You run into a bug. You see the ball moving around. You run into a bug. And what do you typically see? Some sort of a printout in the console that says like error. Really what you want to see something in the brick space that shows you what's wrong, right? You don't want to see a printout in the console. You want to visualize, or you want to see the bug and in the space in which it's happening. That's what that statement is talking about. That's what this statement is saying, right? And these guidelines are inspired by experience in industry and academia. There is actually related reading on this topic. You can actually find research papers and books, book chapters on the related topics. There's nothing quite exactly like what we're talking about today, though. So the first guideline is to visualize tests and comparisons, right? A lot of what you do in software involves tests and comparisons, like comparing two things if one thing is bigger than another or smaller than another, right? You're always making these comparisons and then making a decision based on a comparison, right? So we can actually use that information and come up with visual ways to visualize tests and comparisons, right? So we can actually show the two objects, like object A and object B at runtime, show them on the screen and see if the comparison behavior is working like we're expecting. Right? You can see those objects if you implement this strategy. So visualizing tests and comparisons informs the developer of A and B are expected, like if you're seeing what you're expecting to compare, firstly, and then the results of the tests, right? So we can verify the results of the comparison visually. This is one example. What we're seeing here is a mesh, right? This is why it's complicated in advance, right? This mesh, you haven't discovered meshes yet from computer graphics. So CAD modeling, right? Computer-aided design. Computer-aided design generates meshes like this, right? That's a huge topic in engineering. And it's computer scientists that write the software for those engineering applications, right? It could be you guys in the future. And this CAD model happens to be the component of an automotive engine, or a model of an automotive engine part, where there's fluid flow inside. And to visualize the fluid flow, we trace streamlines. Those are those colored curves. Streamlines are curves that are everywhere tangent to the flow, right? And it's very easy, for example, to run into bugs or problems when you're developing a streamline tracing algorithm, right? Because you seed the streamline, and then you forward integrate, you interpolate, and then you eventually trace the streamline gradually, point by point. But what can be the bug? Sometimes you have unexpected short streamlines that don't finish, don't complete their path. So we can actually write some visualization algorithms or some test and comparison examples that show the current streamline point, for example, show the next streamline point, and then show the cell that they're in, right, as part of our streamline tracing algorithm. And just to make that clear, I know that's hard to follow what I just said, by the way. I have a demo. So here's that process in action, actually, using this strategy, using this debugging strategy. So these are streamlines being traced, and that's that small sphere or dot is the current position on the streamline, and then there are squares appearing. That's the grid cell under the underlying grid cell in which the current stream position is being computed. So we're visualizing the path of the streamline as it's being computed, and we're also showing the underlying grid structure that we're using to retrieve the data, because the data is stored on a grid. And now we can see, okay, is this algorithm behaving the way we think it's supposed to behave? Like, is the streamlines being traced the way we think they're supposed to be traced? And so on, and we can see it step by step. This is an example of a visual debugging technique, so visualizing tests and comparisons. Can anybody think of how this might apply to your coursework? That's a difficult question. Beatrice, right?
Yeah. This is just an attempt, it's not.
Yes, it's a
The
difficult
movement
question.
of the ball, like against the panel and towards the bricks, you could visualize it in the same cell by cell.
Very good, exactly. You have something very similar in the coursework. You have a ball, it's traversing a path, right? And you could visualize, for example, the path itself, and you could also visualize the space around the ball to see when it collides with a brick, right? You can actually visualize that test. Like, is the ball close enough to the brick in order for it to collide, for example? You can actually visualize that and show that. Right, so that's an example. And when I was looking at this, I was thinking also, like, imagine a version of bricks where the ball doesn't go in a straight line, right? It curves. That would be that could be a very difficult version of the bricks game. Anyways, good. So I didn't lose everybody. Visualize data structure, traversal, and evolution. Oops. That's funny. Visualize data structure, traversal, and evolution. So almost all algorithms involve one or more data structures. We can visualize the data structures themselves to see if they're behaving and evolving the way we expect them to, right? As they change over time, as you build them up, for example, as you add data to them or take data from them. Right, you've all seen binary trees. Have you guys seen binary trees yet? Or is that too early? Is it, you've seen binary trees? You can visualize, you can show trees, like you can actually show them and then look at their behavior, right? This image is an example of a clustering algorithm, and there's a green square here. That's the current square. So we're clustering the data one square at a time. You don't see it in this still image, but we're actually moving from left to right, and it's making comparisons with its neighbors to see which one of its neighbors is a good candidate to cluster with. And those are the red squares around the current square. So that's just an example of showing a clustering algorithm as it's being built. Unfortunately, I don't have an animation of that one. This one's advanced. This one's called a quad tree. Has anybody heard of a quad tree before? You can kind of see what's going on there if you look at it. That quad tree is a spatial data structure, and it summarizes data in space, right? But if you have big empty space like here, you don't want to store all the data because it's very redundant. It's just the same data appearing over and over again. So the quad tree represents a large space with a large square, a large quad. And then as the data becomes more and more fine, let's say, or higher resolution, the squares get smaller, so they change in their size, right? So here along the coast, the squares get very, very small so that they can represent the coastline. That's a map, the coastline in an accurate manner. Anyways, that's an example. The quad tree is a very common data structure. You haven't looked at it yet, but you might see it next year, for example. It's very common in computer graphics. It's very common in image processing. It's very common in data visualization, for example. And we can look at the quad tree to see if it's behaving the way we expect it to behave. In this case, it is, right? We have a large empty space here, so we don't store too much data here. And then as we get closer and closer to the coast, we store more and more data, right? So it looks like the way it's supposed to look. Another visual debugging guideline is to classify and color map. So classify and color map geometric primitives in visualization. What do I mean by geometric primitives? I mean things like squares, rectangles, triangles, edges, lines, points, maybe tetrahedra. And probably anybody here what a tetrahedra know what a tetrahedra is? Has anybody heard that word before? Tetrahedra is a pyramid shape, right? It's a 3D triangle, three-dimensional triangle. Cubes could be another example. Textures, circles. That's what I mean by the smallest unit of display. Data has different attributes and values that can be used for debugging. So this is an example. Here's another mesh, right? This is a mesh. We don't really know what it is. It doesn't really matter, and it happens to be a stream surface, but that's not important. The mesh is composed of quads, four-sided polygons. And as a visual debugging strategy, we've color-coded those quads based on different properties. So the quads that are showing divergent properties, in other words, they're spreading, those are colored blue. The quads that show convergent properties, that are moving together, that are getting squashed together, are colored in red. But there are none in that image, actually. I can see there are no red quads there. The quads that have this left rotating behavior are shown in yellow. The quads that have a right rotation behavior are shown in orange. And then quads that are laminar, in other words, they're not rotating left, they're not rotating right, they're just straight. Those are shown in green. But that's a great way to visualize the properties of geometric primitives, right? Is to classify them and color map them so we can see if they're reflecting the behavior that we expect, right? Okay. Does anybody think this is fun? This is skipping ahead into year 3 and 4 and 5 a little bit. Incorporate algorithm parameters into user interface. This is a great one. This is a really great one. I use these all the time, by the way. So new algorithms introduce new parameters like threshold values, min and max values, alpha values, special distances, for example. Identify, discuss, and visualize these new parameters over a range of values. So there are lots of algorithm parameter values that you don't really know very well ahead of time before you've developed the algorithm. If you have a parameter that you don't really understand and you're not sure about the best value for, a threshold value, for example, you can add it to the user interface and then the user can adjust it. So in the example, in the coursework example, can anybody think of an algorithm parameter that you might not be sure of in your coursework, in the bricks coursework? There is one that you might not be sure of, and it's given to you in the coursework, like here's the value that we've chosen, but you could actually adjust the value and explore the value, and maybe if it wasn't given to you in the first instance, you might have to refine it or adjust it. It's the distance between the ball and the brick that defines a collision, right? That there's a distance there between the ball and the brick that defines a collision. That's an algorithm parameter, actually. Somebody has chosen this threshold distance and said, okay, this is what I'm going to define a collision as. If you weren't, somebody did some testing to come up with that threshold value. You didn't see how they came up with that value. They just tested it and tested it and tested it, and then published the software. You didn't see the process that they went through to get that value. But if you're developing software that has threshold values, you can add it to the user interface and let the user change it and see what happens to the program to the program behavior when the user changes it. And then when you get the behavior you want, you take it out of the user interface and you put it into the code, so to speak. Does that make sense, hopefully? And that's true about all algorithm parameters, right? It happens a lot that you don't know the optimal value of something while you're developing the software. In this example, there's a DSEP parameter. That's the distance of separation between streamlines, right? That's an actual algorithm parameter, and that's something that can be adjusted by the user. So when the DSEP is small, the streamlines get really close together, and when the DSEP is big, they spread apart. Five is run simple error checks. This is a good one. It's not that visual, actually. This is something that can be applied to any software. It's not just visual style software. Don't forget to run simple sanity checks on visualization primitives and data structures. This sentence could also read, don't forget to run simple sanity checks on any software. Right? It doesn't have to be visualization software. A simple generic error checking procedure can run through the data objects and check basic properties, point locations, edge lengths, minimum, average, and maximum data values, and boundary conditions. Right? You can, I'm trying to think of an example that might apply to the coursework. But like a very simple error checking procedure could check all the high scores and make sure that none of them are negative, for example. Nobody should have a high score of -10, right? or a simple error check that makes sure that the ball doesn't go out of the boundary. That would be a funny version of bricks too, by the way. A version where the ball can pass through the wall and come out the other side. That would be a funny feature of the bricks game. So the idea is to test every object and just make sure the data values stored in the class variables all fall within a reasonable range. Like the high score should be between 0 and 10,000, for example, or the number of bricks should always be between 0 and 100, for example, or the ball position should never be 1,000,000 in the y direction and minus 1,000,000 in the z direction or the x direction, for example. It's just a simple error check that you can say, okay, run error check, and it tests all the objects and gives a report back, right? That's a very useful debugging tactic. And you can imagine, it's not very difficult to imagine having a method that you have in any object that's just called error check, and it's the object checks its own data attribute, its own member variables to see if they're within reasonable bounds. Here's an example from my master's thesis, actually, I was working on. Unfortunately, I don't have an image here. Anyways, I was working on a surface construction algorithm, and it was supposed to represent surfaces at multiple resolutions. For example, 9 cubed resolution, or 64 cubed resolution, or 128 cubed resolution, or 256 cubed resolution. And I had a strange bug. The surface looked accurate and everything was fine if I rendered it at 64 cubed resolution. It was fine. But as soon as I switched to 128 cubed resolution, suddenly everything went sour, like there was a massive bug. Everything went wrong. And that's hard to find. When you're going from a data set that's 64 cubed to a data set that's 128 cubed, that's kind of a lot of data. It's not something you can't just run printf on that data set and try to find the error. Well, you might be able to if you have a special brain. But a better idea would be to run a simple error check. So cracks appeared in my surfaces only at the 128 cubed resolution data or greater. So to track down the error, I just implemented a simple generic error checking procedure. And all it did was it looked at the locations of all the triangle vertices that make the surface, because surfaces are made of triangles in computer graphics, and see if they were inside their associated cube. That's all I did, because every triangle was inside of a cube or part of a cube in 3D space. And then I also checked that the minimum and maximum data values of every node in the octree that's getting more advanced fell within their expected range. I won't really talk about what an octree is in detail, but does everybody remember the quad tree from a few slides ago? An octree is that same idea, but expanded into 3 dimensions. So it's a tricky data structure. And the values were recomputed from scratch and compared to the stored values, and then this function was traverse the entire octree and could be called at any time. Right, so I could just hit error check and see if all of the data seemed to be having the expected values. A very common bug that comes up in Gesundheit, a very common bug that comes up in computer graphics is shading. So if anybody takes computer graphics later on, you render surfaces and you apply shading to them to make them look shiny. That's often a source of bugs. And you can render the surface normals to discover lighting and shading bugs. The surface normals are these tangent vectors to the surfaces that point directly out from the surface. And those are required for the shading to work properly. Okay, introduce a step function. This one applies to the coursework, the current coursework. Algorithms involve computation that iterates several times, perhaps over each data item, and again, over each pass over the data structure, any data structure. So incorporate a feature in the user interface that interrupts or pauses execution between each iteration of the algorithm processing. How would that apply to this coursework? This coursework is not very big, but imagine you were doing a bricks game and it had to be sold in stores like Toys R Us or whatever, and you had to bring it up to the commercial level and you had to make it really interesting and advanced, right? Then you might have to get more serious about your debugging. Can anybody imagine how this would apply to the bricks game and the coursework? It is an advanced question. So imagine you have a ball and it's bouncing around, but it's not bouncing the way it's supposed to. Like maybe the ball bounces too early. It doesn't hit the wall properly, or maybe it moves past the wall by accident. Or maybe it hits a brick, but the brick doesn't break the way it's expected to break, right? You could introduce a pause function into the software where you hit the space bar and the game just freezes, right? So you can see like it, and then every time you hit the space button, the ball moves 1 unit or 1 frame, and then you hit it again, it moves 1 frame. So you basically, what you're doing is you're slowing down the game so you can really see what's happening and it's not too fast for you, for example. Yeah, that's how this could be applied to the coursework. It's not necessary because you've already been given a game that's working on some level. But whoever developed the game in the first place may have had a function like this before while they were developing it to slow it down. Any program that involves animation, this could be a useful debugging strategy. So the user can pause the current scene and look in more detail. Pressing the pause button again then executes exactly 1 loop of the algorithm. So it moves the ball by 1 unit, for example. The user may then step to the program execution at runtime 1 iteration at a time. Yeah. Very common. In fact, everybody here has met Wong, right? One of the teaching assistants in the lab, right? I just asked him to incorporate a step function into his software that we're working on as part of his PhD. Make use of still image-driven animation. This is a funny one. Sometimes you have a bug that occurs very rarely. It's very rare. It happens like 1 in 1,000 times or 1 in 10,000 times or something like that. So it's difficult to track down. It takes a lot of time and it's difficult to reproduce. Like, it's one of those bugs that only occurs when you're sitting alone or you're trying to show it to an audience, but it doesn't happen when you want it to happen, right? Some bugs occur very infrequently, only after several time steps have been processed and visualized. You might be watching an animation of your own game in action and notice bugs only after several seconds or even minutes. Like in your bricks game, you might notice that there's a new bug that occurs only after the ball has hit like 20 bricks, and then suddenly something very strange happens. The point, imagine you did have a bug that only appeared after 20 bricks got hit, right? Imagine you're staring at your game, or you're playing your game, and you hit the 20th brick, but you don't know it's the 20th brick that causes the bug. And you just don't pay attention for 1 second. You look away for 1 second, or you blink for 1 second, and you miss the bug, right? But you had to wait until 20 bricks got destroyed to see the bug, right? That's a horrible situation to be in, because then you have to start over and be like, oh, I have to pay attention at the 20th brick to see what just happened. So this is making use of still image driven animation. So you can actually, every frame, for every animated frame of your program, you can just save a still image. You can do a screen capture or build a function into your software that says save image, like save this game image. So you run 1 frame of animation and then you save a still image. Run 1 frame, save a still image automatically rather than manually. This is not as necessary now as it used to be. Today, what's an easier version of this function? There's an easier way to implement this function than actually writing it into the software. Does anybody know? You can just use screen capturing software now. When I published this article, screen capturing software was not so popular or freely available. But now, if you run into a bug like that, like your bricks program only crashes after the 20th brick, you can just, screen capture, if the whole computer crashes after the 20th brick, then maybe a screen capture program is not going to work. But the still image-driven animation might still work. That's saving the images to files after each frame. But typically now, you would just hit the screen capture, hit screen record, and then capture the bug that way. And this might not be so necessary anymore. And then watch the screen capture back again. I used to have a function, for example, in my software that would automatically resize the image to 512 by 512 pixels automatically, and then save every frame of the animation to a file. So that if it crashed after 5 minutes, I could go back through the set of still images and watch them to see exactly where and why it crashed. Right? And you can play back still images in lots of different pieces of software, right? Adobe Premiere plays back still images. VideoMock does. File browsers do. Like the Windows file browser plays back still images, and so does the Mac file browser. Okay, this is something everybody can understand, right? Test your algorithms and your software on a variety of data sets. That's not exactly true for this coursework. You don't have lots of data sets to test. But in the real world, you do write software with lots of data, and you want to test your software on lots of data sets. That's actually what James was talking about on Tuesday. His company generates data sets that you can use to test your software, right? That's what his company excels at, right? So he's dedicated a whole company to this concept, to this idea. And of course, he's going to get very, very wealthy through that innovation. right? You can create your own synthetic data with known characteristics. Find the smallest data set that creates a problem. If you have a bug associated with data, you can create this, you try to create the smallest data set possible that generates the bug. And then after that's working, you test your algorithms and your software on big, complicated data sets and test on a variety of data sets. This is a very obvious debugging technique, but it's very often overlooked, very often. Yeah. Exploit and compare with previous literature. There's a good chance that whatever you're working on has been done before or looked at before. So the idea here is to look at what people have done before you in the same context or working on the same problem. Right? It may be published in a book. It might be published in a paper, in a research paper. In your case, in the bricks game, that's going to be published. That could be published where? Any idea? Where could you find other brick games? If you wanted to compare your brick game with other brick games, where could you find some other brick games? Anyone? If you want to compare your brick game to someone else's, where would you find other brick games? Anybody know? Was everybody asleep? This is an easy question. Beatrice?
Just online, sort of. I mean, you can find them sort of on the App Store on your phone. You can find them just on the internet because it's such a popular.
That's correct. That's right. Google can help you find them. YouTube, right? Brick game into YouTube. Brick game into GitHub, right? You'll find lots of them. So you can compare your program with other people's programs. This is something that a lot of people don't think about when they're trying to develop their own software or debug their software. Like, how did someone else handle this? Or what does this look like on somebody else's program, right? So I've seen this overlooked very often, this strategy. Make exclusive use of accessor methods. Hopefully everybody's heard me say that a million times already, right? It's because accessor methods perform error checking. Every time you call a set method, it checks for errors. Like, is the value you're setting within the proper range, right? Is it above the minimum? Is it below the maximum? For example, is the string length reasonable? Is somebody trying to set their username to a string that's 5,000 words long? You should be checking for that, right? Every string has a maximum length. Every string has a minimum length, right? As well. If somebody tries to set their username to 0, a string of 0, that's not good either, right? So every set method performs very simple sanity checks, right? Is somebody trying to set the high score to -10? You should be checking for that, actually. Or is the high score 1 billion? Like, what is the maximum high score? You actually want to check that. Like, how many bricks can somebody hit, right? You have a reasonable maximum score. Follow coding conventions, everybody knows this. This is a very funny one, by the way. If you run into a bug, a strange problem, just tell somebody else about it. Just tell somebody. Say, I have this bug. Okay, we should stop now. And the process of just telling it to somebody else, you'll often discover the bug. Like, it'll often appear in your head. Okay, any questions? We should stop because there's another class after this one. If you're interested in reading more, there is a paper on this topic that I'll put onto